if we can go to the next speaker, it's our great pleasure to have Dr. Bruce Boghosian from Tufts University. I don't know if the slides are there. Yeah, that's great.
Are you able to see?
Absolutely.
Let me see if I can enter full screen. Okay.
Yeah, thank you. And Professor Boghosian will talk about new developments in agent-based models of wealth distribution.
Okay, thank you very much. Just as a quick outline of my talk, I'll begin with a description of wealth distributions and then introduce the asset exchange models that will be the topic of the rest of the talk. I'll first talk about their steady state solutions and then their dynamic properties before coming to some conclusions. So first, what is the fundamental thing that we're after here? It's the agent density function. It's a function we're going to assume wealth is positive, so it starts off at a wealth of 0. And the integral of this function between A and B, the area under the curve, the shaded area there, is then the number of agents with wealth in the interval from A to B. So initially we'll take wealth greater than 0, but there's no reason that the origin here, there's no reason that the origin here has to be 0. We'll discuss that later. If I take the integral from 0 to infinity of this thing, I get the total number of agents, which is an extensive variable. If I take the first moment integrating from 0 to infinity of p times w, I will get the total wealth, which is also an extensive variable. The mean wealth is then the ratio of those two things, and we'll denote that by mu, and it's an intensive variable. Everybody can still see the screen?
Yes.
Okay, good.
Yeah. Yeah.
I wasn't sure because the screen looks different now. There's two other things I'd like to define here. One is a function that Pareto looked at a century ago. It's the fraction of agents with wealth less than W. So we're going to take the area under the curve of P from 0 to W and divide by the total number of agents. So that's the fraction of agents who have wealth less than W. And L is the fraction of wealth held by agents with wealth less than W, defined in a very similar way. And the American economist Max Lorenz in the early 20th century had the idea of making a parametric plot where you plot the fraction of people versus the fraction of wealth. And you can see on the screen here that, you know, in a society where everybody had exactly the same wealth, well, 0% of the people would have 0% of the wealth, 50% of the people would have 50% of the wealth, 100% of the people would have 100% of the wealth, and you'd get an absolutely straight diagonal line. Let's go to the opposite extreme. Suppose you had a complete oligarchy. One person had all the wealth. Well, then 25% of the people would have 0% of the wealth. 75% of the people would have 0% of the wealth. And it's only when you got to 1 that the thing would jump up discontinuously to the upper corner, 1, 1. And that's a green curve that you might have difficulty seeing in the lower right-hand corner. Real Lorenz curves tend to look like this orange one in the middle somewhere. It's fairly easy to show that it has to lie below the diagonal. It has to be concave up. Only a little more difficult to show that if you know the Lorenz curve, this function I'm calling script L, and if you know the extensive variables, you can reconstruct the agent density function. So, you know, the top of the screen here shows that if you know the agent density function, you can get the Lorenz curve. You can also go backwards as well. So the Lorenz curve is often the more elucidating thing to look at. This is an actual Lorenz curve for the United States. This is household wealth distribution collected by the Survey of Consumer Finances of the Federal Reserve Bank. This was 2013 data. Two things I'd like to point out about it. About 30%, if we look at the upper tail here, about 30% of US wealth is held by very nearly 0 people. Obviously, it can't be 0, but it does look like this curve is hitting the right-hand side below 1. Obviously, that's being a bit fast and loose. There is some air in there, but not much. If you go to the other end of the curve, about 30% of people have an amount of wealth that's pretty well approximated by 0. And that comes from the fact that if you look closely at the red curve on the left, it dips down before it goes up. And that's due to the fact that about 10.5% of the population, or 11% somewhere in there, have negative wealth. And it's not until you get up to the high 20% that you're back up to 0 again. Remember, this is cumulative. It's not until about 27, 30% somewhere in there that you have a net wealth of 0. So the lowest 30% have a net wealth of 0. By the way, that doesn't mean they all live in poverty. Somebody who recently graduated from medical school and has lots of student debts might register as having negative wealth here, according to the way that the SCF collects data. Now let me switch to, how do we describe this quantitatively? Let me first talk about the spirit in which we're going to try to model this. And it's the same spirit that's used for the Ising model of ferromagnetism. We're going to try to come up with an idealized dynamics at the microscopic level that gives some realistic phenomenology. And even though the Ising model is a very idealized approximation to true magnetic domains, the Ising model in 2 dimensions, say, is on a square lattice. Regular magnetic domains are really very irregular shaped. And yet, look, the graph on the left here shows magnetism versus temperature for a real material. And on the right, what you're seeing is Onsaga's solution to the Ising model in 2 dimensions as a function of temperature. And you have to be pretty jaded to say that one isn't doesn't provide a reasonable understanding of the other, even though it's extremely idealized at the microscopic level. That's what we're after. So we begin with what's come to be called the yard cell model due to Anirban Chakraborty's work in the early 2000s. He looked at a set of agents. The agents each have a certain amount of wealth. They engage in wealth-conserving transactions with one another. You pick 2 agents randomly. Let's say they have wealth W and X. An amount of wealth delta W exchanges between them. So W has delta W added to it, and the transaction partner X has delta W subtracted from it. Now, delta W can be positive or negative. So wealth here could go in one direction or the other. And the sign of delta W, we're going to say, is decided by the flip of a fair coin. But we're also going to say that wealth can never become negative. So we're going to demand that the amount of the magnitude of delta W be smaller than the wealth of the poorer of the 2 agents. So we're going to say it's proportional to the minimum of the minimum of W and X. And that proportionality constant for random walk reasons goes as the square root of delta T, where delta T is the time of one transaction. Eta determines which direction the wealth moves in. It's either -1 or 1. Fair coin, it has expectation value 0. The remarkable thing is that even though the coin is fair, what Chakraborty found is that all of the wealth will concentrate into the hands of one agent. This is a real Monte Carlo simulation of that, where you start with 10 agents, each of which has 1 unit of wealth. You run it forward in time, and this is log wealth versus time. So except for the wealthiest agent, who mops up all the wealth, all of the rest of the agents see their wealth decreasing on average exponentially in time. If you were to do a continuum limit of this, an ensemble average or a delta T goes to 0 limit, letting the number of transactions become large, it looks something like this. It becomes smooth. You can still see that for the wealthiest agent, the initial endowment of 1 or 10 to the 0 becomes 10 to the 1. Everybody else is on their way down. And you can demonstrate by an easy argument that in the time asymptotic limit, they're all losing exponentially. To make this more rigorous is not that easy. For the Boltzmann and the Fokker-Planck equations for that process, we showed in 2015 that the Gini coefficient effectively functions as like Boltzmann's H theorem. It's guaranteed to increase the Gini, this dynamics, when it's away from equilibrium, and its equilibrium is one where the Gini is 1. 1 year later, Christophe Chorot at the Sorbonne demonstrated that even for the underlying statistical process, G approaches 1 almost surely in the technical sense of that term. So just a quick point, though the rule seems fair, it contains an endogenous downward pressure on all the poorer agents. People would argue that if they have an equal chance of winning and losing, it's not that unreasonable to engage in the transaction. And yet there's a downward pressure. It is just a trickle, but we would argue that if you multiply this downward pressure by 7.6 billion people in the world conducting quadrillions or even quintillions of transactions per year, the trickle becomes a torrent. And in the absence of redistribution, it precludes a supply-demand steady state. So how do we fix this model? We want to use this as our 0th order approximation. We're going to make 3 modifications to it. One of them, I just want to keep my eye on the time. One of them is we'll introduce redistribution. We'll essentially tax the wealth of all the transacting agents at some fixed rate per unit time per unit wealth. And we will redistribute that in even shares to everybody. And this adds a second term to the statistical process. And you can see that anybody below the mean wealth is going to receive net wealth due to this redistribution, and everybody above it will lose some net wealth due to this redistribution. Second modification. Suppose the coin flip is not fair, but favors the wealthier agent. We call this wealth-attained advantage. And the reasons for it are clear in society. Wealthier agents attain higher percentage rates on investments. They receive better financial advice. They avoid taxation more effectively. They can even influence legislation to their benefit. Poorer agents have less time to shop for the best prices, pay higher interest rates, sometimes high rents. How do we model this? We bias the coin a little bit. We bias it by the difference in wealth normalized to the mean wealth. This coefficient in front controls the level of wealth-attained advantage. So we have now 2 coefficients in the model, chi, which denotes the level of redistribution, zeta, wealth-attained advantage. One can derive a Fokker-Planck equation for this process. Chi and zeta appear in the drift term of the Fokker-Planck equation. That gamma that you saw in the initial Chakraborty model determines the time scale and sits in front of the delta t term. To find a steady state of this, you would set dp dt equal to 0 and then integrate once in W to get an ordinary differential equation. This is harder to solve than it looks because the drift and diffusion coefficients are both functionals of the unknown distribution P. And therefore, this is a quadratically nonlinear and non-local differential equation, but we've learned how to solve it numerically, and it's much more efficient than doing Monte Carlo simulations. Has a very interesting property. If wealth-attained advantage is less than redistribution, the Lorenz curve does begin at 0, 0 and end at 1, 1. But if it's greater, we call this the supercritical case, it ends at a number less than 1, 1. In other words, it ends at a value of chi over zeta in which case 1 minus chi over zeta fraction of the wealth is now held by a partial oligarchy. In other words, this exhibits what Jean-Philippe Bouchot and Marc Nezad called wealth condensation in their 2000 paper. It's a natural second order phase transition that comes from this model. Another way to show it is if I plot the fraction, we'll call this C, the fraction of wealth held by the wealthiest agent, as a function of zeta over chi. It goes from something that would be 0 in the large agent limit to something that is non-zero abruptly when this quantity passes 1. One other thing that this exhibits is duality. If you're familiar with Kramers-Vannier duality in the Ising model, this has a similar feature. If I were to swap chi and zeta, then since criticality happens when zeta is equal to chi, if I swap the two of them, I go from a supercritical state to a subcritical state. So the supercritical state might be the dotted Lorenz curve down there with a partial oligarchy. The subcritical state is the solid one. It's a rigorous result that if I simply rescale the solid one, I can get the dotted one. Just remove the oligarchy and rescale the curve. And that's an exact result. It's one of the few exact results we have for the model. This brings us to a third modification, which is to include negative agents. And to do this, we simply shift the agent density function so that instead of starting at 0, it starts at the negative of some multiple lambda of the mean wealth, and then goes off to infinity. That actually is more than just curve fitting. It can be brought down to the microscopic level, and the transaction can be redefined to incorporate lambda as a parameter. So this still has an idealized micro foundation. With this 3-parameter model, the red curve is the Survey of Consumer Finance's curve I showed you earlier. The blue curve, the dotted blue curve, is a solution to this model we call the Affine wealth model for these 3 parameters. The average error of fitting in this case is less than 0.21 we can do the same thing going back through 30 years of Survey of Consumer Finance's data. We can also do the same thing for many different countries. We've looked, for example, at European Central Bank countries. Just one quick note, this black dashed line at about 70% represents the partial oligarchy present in the exact solution to the equation. So even though the red curve can't hit the right-hand side of this figure, the closest solution to the affine wealth model that it matches does hit the right-hand side. And in that sense, we can say that the US is a partial oligarchy with about 30% of the wealth held by basically 0 of the population. Most countries,
another 2 minutes, please.
Okay, I'll wrap it up. Most countries in the world are just above criticality. Somehow the Netherlands comes out just below criticality. I don't know what they're doing. Everybody else is just above criticality, which is already kind of interesting. Finally, some time-dependent results. One of them is that the fraction of wealth held by the oligarchy obeys, and again, this is an exact result independent of the initial conditions of the distribution. It obeys a logistic equation. And this undergoes a transcritical bifurcation when zeta over chi passes through 1. It goes from an equilibrium state of 0% of the wealth held by the oligarchy to 1 minus chi over zeta % of the wealth held by the oligarchy. A second dynamical result we can get is upward mobility. You may have seen the study a few years ago that showed that the 900 wealthiest families in Florence, by looking at tax records, you can see that the same surnames are among the wealthiest families today, or at least there's a very positive correlation. between the surnames and the wealth. We're able to look at first passage times once you have a Fokker-Planck equation. The expected time of transition from a wealth A to a wealth B is given by an exact expression. So we can actually look at the time it takes to go from the middle of the first percentile to the middle of the fourth decile, that is. That's maybe 3 years. To get to the 9th decile, the middle of that, it takes a lifetime of hard work, maybe 54 years. To get to the middle of the 10th decile takes centuries. And it doesn't help you much to go from the 8th decile to the 10th decile. Still takes centuries to get up to that, if, of course, the US had been in steady state all that time, which, of course, it hasn't. Finally, you can look at movement on the wealth spectrum. You can look at wealth flux and agent flux. And once you have a time-dependent solution, you can back those out. Now, the mean wealth in the US today is about 700K. If that sounds high, you're forgetting the difference between mean and median. Median wealth is well under $100,000 for a household, but mean wealth is 700K. And now, by looking at these fluxes, we can test what's called trickle-down theory. People trickle down if their wealth is less than or equal to about 6 mu, or about $4.2 million. Above that, they trickle up. Wealth, on the other hand, if you're a dollar bill, which direction do you go in? Well, if you're held by somebody with wealth above mu, you trickle up. If below mu, you trickle down, but only because so many people are trickling down, carrying the wealth with them. So in conclusion, these are simple mathematical models of wealth distribution. In spite of their simplicity, they're accurate and provide insight. They challenge the economic orthodoxy of supply-demand equilibrium and suggest that we need to rethink our attitudes about wealth in many different ways. Sorry for going over.
Thank you very much, Dr. Boghosian. I don't think we have any time for questions, but that depends though, because I don't know if the next speaker, Dr. Chakrabarty, is out there on waiting for his talk, because somehow the organizers say he's not there, but I'm not sure if he's under an alias we can read in the participants list. And I don't, Dr. Chakrabarty, are you there? Right, so what I propose is that maybe we can leave some question time now, and then have Dr. Ali Bek come in once that sort of question time is finished. So maybe Dr. Abel and Dr. Boghosian, if there are any questions for any of the two speakers, does anybody have any questions for the two speakers?
Well, I have not a question. I have asking for papers of the work. Can you, like very much the one Boghosian, I would love to read more about it. So if you can send us a reference for this work, I would appreciate it.
Certainly, I'd be happy to do that. How shall I do that? To whom shall I?
Just put it on the chat, or you send it to my email, I don't know. Or just you say it right now. What's the best paper to read?
Let's see. There are two papers that are in both, 3 papers in Physica A over the past 3 years. I think if you search Physica A and search me as an author, you'll find at least 3 of them. One of them on the affine wealth model, one of them on duality, and one of them on the version of the model without negative agents.
Thank you. Thank you.
Yeah, may I suggest, Bruce, you can post your talk, right? PowerPoint, a PDF, right? On the conference website, right?
Oh, yes.
Bruce?
Oh.
Yes, and I suppose your talk has references to your papers, right? Or it should have references, right?
I can add them, yeah.
Yeah, in other words, people can just look at your slides of your presentation, can download slides of your presentation from the conference site, and that slide should have references for those who need them. Okay. Yeah. I just want to mention, just organizational, are we sure the 4th speaker is also present? I don't see his name in the list of participants.
Yeah.
It seems to me both. It looks
Good
like
question.
both. Yeah, third and fourth speakers they seem to be missing anyway. So
Victor,
yes,
fourth speaker is in the room.
is in the room. Okay, good. Good to know. I mean, yeah, boundary conditions. Okay.
I have a question. And this, I wonder if there's a connection with Victor, with what you presented yesterday when I was in the session that I chaired, and with the payments to capital accruing to the upper percent of the society, and if that point in the Fokker-Planck equation of that transition from the thermal part of the society into the Pareto distribution part of the society, if that's not tied in with what that critical point is. I'm trying to understand if there's a potential mathematical connection with that.
I guess you're asking whether there's connection between what I presented in my talk,
yes,
and Bruce's talk, the oligarchy, right?
Yes.
Yes. Okay, that's absolutely a very great question, because what happened is that yesterday I didn't have time to show one slide, so let me just sketch the slide. So to make connection, I open a whiteboard and I draw with my finger. So there is this. There is a Lorenz curve, right? Okay. So with this two-class distribution that I discussed in my talk, we can generate Lorenz curve. I actually have this slide. If you download slides of my talk from the conference site, there is a slide which I didn't show because I didn't have time. And the Lorenz curve looks like this. Okay. So I mean, this part, I mean, maybe I should use this color. So this part is the Lorenz curve for the exponential distribution. And then this part is kind of the upper class. And upper class, very much like in Bruce's talk, the upper class corresponds to very small, few percent of population, but corresponds to big, fraction, maybe 20% or so. I mean, depends. Okay. So point is, the Lorenz curve for this two-class distribution that I showed looks very similar to the kind of Lorenz curve that Bruce showed in his talk. So I think they're basically qualitatively consistent and kind of describe more or less the same thing. There are some kind of, if you like, minor technical differences, which I don't think are fundamentally important. So in my description, in my presentation, I looked at, cumulative distribution function, the data, and I argued that it seemed to show that this part is described by power law. Okay. Whereas in Bruce's case, when oligarchy forms, there's no statement how it is described. It's just a condensate. It's a condensate, but there is no explicit mathematical statement whether it's described by any particular function. So that's kind of technical difference, right? But it may be not so important, because in both cases, in both models, that upper, significant upper share is owned by small percentage of population. And at the end of the day, it may be not terribly important whether this part is described by power law or not, because for one thing, nobody knows how far it extends. There was some proposal, maybe it's not a single power law, maybe it's like two power laws. Is it even a power law at all? So at the end of the day, it's not terribly important. What is important is that a small fraction of population owns as a finite amount of wealth or income. And that is basically what Bruce calls oligarchy or condensation. So I would say they're qualitatively consistent, although there is some minor technical mathematical kind of details, differences maybe.
The mathematical detail in the continuum limit, this only makes a difference, but it turns out to be interesting, because we were wondering back in the world of agent density functions, what does that end up looking like in the limit where it really is a condensate? And it's a marvelous object. It's what mathematicians would call a distribution, just like the Dirac delta distribution, except it's very different from the Dirac delta. If the Dirac delta at wealth of 0 corresponds to one agent with 0 wealth, this distributional object corresponds to one unit of wealth so far out that there is 0 agents. And it turns out that you can use rigorous Sobolev-Schwartz distribution theory to make sense of that. But it's a mathematical object that just hasn't been written about before. which, you know, from the view of functional analysis makes it interesting. But I think you're quite right that the difference out there is, if you're not a mathematician, you don't care about the difference so much.